Okay. We can talk about anything you want to talk about after class. Okay, so I hope you felt that the test was at least fair. I think there was one or two problems that were a little challenging in terms of algebra, but other than that, I hope that everything you looked at was something that you at least felt like you saw in the review. Yeah? No? Yes? Okay. Not many of you reached out for help since I saw you on Thursday. I had a few students contact me, but not a whole lot of people reached out for help on any of the problems on the review. So please, again, if I give you a review, if you don't know how to do something or you need some clarification, reach out. All right, well, let's do this. We are in chapter 2, just a recap of what we've done. We started out with the idea of the derivative, right? This idea of this derivative, slope of a tangent line. And then we extended this idea into looking at the derivative as this new function that we can create. And then in last class, 2.3, we said, hey, we can finally do away with the limit. No more limits. We're going to use these shortcuts, right? And I gave you all those basic differentiation formulas, right? And now we need to move into these 3 sessions. We're not going to do all 3 today. We're just going to do as much as we can from 2.4. Product rule and quotient rule. So here's how we're going to do this. We're going to start with a problem. I'm actually going to give us a problem to look at. Having trouble signing. 2.4. 2.4. So I'd like for us to consider the following. If I tell you f of x is x squared, what's the derivative of that and why? 2x. That's it, right? 2x, why? What rule are you using? Do you know what it's called? Power rule. Power rule. That's the power rule, right? No more limits, shortcut, right? Just bring the 2 out, x to the first power, right? We don't need to write the first power. That's our power rule, right? We're all happy with that? Okay, now let me give you another function. Let's call it g of x. And I'm going to let that be sine x. Do you know what the derivative of that is? Cosine x. Why? I told you last class, right, that the derivative of sine x is cosine x. And I tried to prove it to you. Actually, I did prove this one. Proved it geometrically, and I proved it using some pre-cal formulas. So we know that the derivative of this, which I would write g prime of x, is cosine x, right? Okay, that we know. So let's consider this new problem. Let's say I give you this new function. I'm going to call it, I don't know, I'm going to call it h of x. F, g, right? H seems natural. And it's going to be x squared times sine x. Now, I'm not writing a multiplication symbol in between the two. I think it's understood, it's implied that there's multiplication between those, right? And the question becomes, what is the derivative of that, right? So the question becomes, what is the derivative? Well, what do you hope it is? What do you hope it would be? 2x times cosine x, right? That's what you would hope it would be. And that's the question, is that the case? Well, it's going to turn out to not be correct. That's not correct, all right? But maybe we can look at the graph. You know how you just took a test where I gave you a function, asked you to graph its derivative, right? So we've had some experience where you look at a function, then you look at its derivative. Let's go to Desmos. And let's graph the original function, x squared times sine x. Okay, that's the original function. We'll look at it in more detail in a second. Then let's look at what we hope the derivative would be, 2x times cosine x. And let's get rid of this, and I'll erase stuff on the board, but Let's just see if this matches up at all. Let me make the blue one's the derivative, right? The blue one is the derivative. So I'm going to make it dotted so that we can distinguish between the two. All right. So can we convince ourselves that the blue one is not the derivative of the red one? Well, let's see. Let me start at a point. Just look at the red one right now. Do you all agree that right here at the origin, right, the slope of the tangent line there should be what? 0. Is the blue function, is the blue curve go through 0? Does it have a y value of 0 there? Yes, so that looks okay, doesn't it? Okay, let's see. Tell me what happens to the slope of the tangent line here as I move to the right. So we're going and it's what? Positive and positive getting bigger, positive getting, is that what the blue one's doing? Positive getting bigger, positive getting bigger, positive getting bigger. What's supposed to keep happening? Positive bigger, positive bigger, positive bigger, positive bigger. Is that what the blue one does? No, the blue one goes up and then it comes back down. And it actually becomes negative, doesn't it? But see, our tangent line is still positive here. So do y'all see it doesn't match? Like it doesn't seem to fit, right? That's just a geometric proof, all right? It's not enough just for me to do that. But I hope you would, by looking at that, be somewhat convinced that what we wish the derivative was is not the case, right? And I will tell you this, that if the original function is x squared sine x, if the derivative was this, we would have becoming an engineer, computer science, getting through all the calculus sequence would be so much easier because that behaves the way you want it to behave, the way that seems normal, right? With limits, remember with limits, when we took a limit of two things being multiplied, we could do the limit of each one individually, but not with derivatives. If I take the derivative of two things being multiplied, this is not what happens. So the natural question then becomes, what does happen, right? What's the correct answer, right? So here's what I'm going to do. I'm going to prove it to you. We're going to go back to the limit, and we're going to do a proof of why the derivative becomes the formula that I'm going to give you. The proof is only important to show you that where the formula comes from, all right? Once I give you the formula, we don't need the proof anymore, right? We don't need the limit. So here's what I'm going to do. If h of x is equal to some function f of x times some other function g of x, find h prime of x. See, we just defined a function h and it was what? X squared times sine, right? X squared times sine. What I'm asking is, if I give you a function and I tell you that it's a product of two functions, what would the derivative be? So here's the definition. The definition of h prime of x is limit h goes to 0, h of x plus h. Ooh, this is kind of bad notation with the multiple h's. Do you all see that? We're going to have h going to 0, but h is the name of our function. Can y'all handle it? You want to go capital H?
Yeah, capital H.
We can go capital H. So let's go capital H here. That way we don't confuse it. Capital H here, capital H here. We only need it for a second. So what is the derivative? All right. Yes? Mm-hmm. So it's that minus capital H of x over little h. Is that not the formula? Do you all see that that's the formula? Remember our generic formula? F prime of x, you needed this on the test, right? Is limit h goes to 0, f of x plus h minus f of x all over h, right? That's our generic formula for the derivative of some function. I'm doing that same formula for the capital H function. So capital H of x plus h, and then minus capital H of x, and then over little h. Yeah? What happens if you plug x plus h into capital H? Well, that means I'd have to plug it in here and here, right? There and there. And then if I plug x into this, I just get those two. So let me write that down. Limit little h goes to 0. I have f of x plus h times g of x plus h minus f of x times g of x, and then all over h. Any questions on what I did there? Plug x plus h into that, plug x into that, subtract the two, right? And then you look at that and you're like, well, what the heck do you do with that, right? The ultimate goal is to try and get an h to cancel, right? That's what we've been doing in the past. What algebra? We don't even know what these functions are, right? I don't want you thinking of x squared and sine x right now. These are supposed to be just generic functions. So mathematicians looked at this for a long time and tried to figure out what this would become. And the next thing that I do right now is one of the most powerful things that mathematicians do, all right? This is what I show you right here. I'm going to realize that in here, there's a hidden zero, all right? A hidden zero. Watch me do it. Okay, I'm going to put it in red, okay? I'm about to add something and subtract something. I'm going to add f of x times g of x plus h, and then I'm subtract the exact same thing. Am I allowed to do that? Can I add 2 and subtract 2 from something? And that would be the same as the original thing, wouldn't it? Now, I'm not done. I still have something else over here. I have f of x times g of x. Right? So right in between these two, right, this minus this is here, that's up here, but in between the two, I introduced a hidden zero. Do y'all see it? Now you might be sitting there going, where in the world did you come up with that, right? Like what made you do this? And I can tell you right now, somebody struggled with this for a long time and finally figured out that's what's going to work, all right? So we're talking about probably like many, many years of thought that humans had to like go through before we figured out that this would work, all right? So I'm going to take that and divide this by h, right? So why did we do that? Whoever came up with this, I don't think anyone has credit for this, like no one person gets the credit for coming up with that hidden zero, but yeah, I'm going to split this up. Right here, right after that second piece, right there before the minus sign, I'm going to split this into 2 separate pieces. All right, so watch. I'm going to have the limit as h goes to 0, and then I'm going to have this and this over h. So it's going to be f of x plus h times g of x plus h. You know what? Let's do it this way. I think this will work out better for us. I can split this up any way I want. I'm going to do this and this one together, all right, next to each other. And then put that over h. And then I'm going to say plus, and now I'm going to do another limit, and I'm going to do the other two. The other two are this one together with that one. All right? So it's going to be f of x times g of x plus h minus f of x, right? F of x, g of x, all over h. Do you all see that that's the same exact problem? Do you all agree that I can do that with fractions? If you have a fraction and you have one thing on the bottom, you can take 2 of them, put it over that denominator, and then these 2 over that. see, if I were to ask you to put those back together, wouldn't they have the same denominator, right? So you just put them back together and the numerators would all go together. Then you could rearrange things, yes? Any questions on that? There's still like, you're sitting there going, why in the hell are you doing this, right? Like what's the point of all this? This is the big eureka moment's about to happen. Limit h goes to 0. All right, so from this, do you all see that they both have a g of x plus h? Do you see that they both have that? I'm going to factor that out and put it in front. So g of x plus h here. And then what's left is an f of x plus h minus f of x, and then over h. So what I did is I took this GCF, greatest common factor, I pulled it out in front of the fraction and just slapped it in the front. And you could just push it back through, right? It would distribute back to both those and we would get that. Do y'all see that? Is that fair? I'm not breaking any rules, algebra rules, that's fair? Okay, on the other one, do you see GCF over here? F of x, okay, let's pull that out. So I'll have plus limit h goes to 0. Okay, this is going to be f of x comes out times, and then here I'll have g of x plus h minus g of x, and then all of that over h. Yeah? Still with me? One more step, and we're there. This is a limit of a product, right? I have multiplication. I can do the limits separately. So this is limit h goes to 0, g of x plus h, times limit h goes to 0, f of x plus h minus f of x all over h, plus limit h goes to 0, f of x times limit h goes to 0 of g of x plus h minus g of x all over h. Is that legal? Limits work that way? If you have product, a limit of a product, you can do the limit of each one, plus limit of a product, do the limit of each one. Okay. You want to tell me what happens next? There seems to be a lot going on that laptop, so.
I'm kind of writing it now.
You writing it? Okay. Do you see anything? Look at each one individually. What happens if h goes to 0 here? You would just get what? Just on this one. G of x? Everyone see that? So do you all agree if I do this limit right now, I just get g of x? Okay, times. Now, this. That limit is really impossible for us to figure out what it is. Like, we can't tell what it is, but what?
It's just the derivative of that.
Yeah, that is the actual definition of what f prime is, isn't it? So would you agree that this right here is just f prime of x? Yes? That's by definition. When we define that, we said that is what f prime of x is. And then what? Plus. Now take this limit. What happens when h goes to 0 here? Well, there is no h here, right? There's no h's. So it's just going to spit out whatever's there, f of x. And then times, yeah, this is this definition, right? But with g, not f. So isn't that g prime of x down at the end? That's it. What's that? That's the formula. Now, let's, yes?
Why is that first part G of X?
Okay, so if h goes to 0, right? If h goes to 0, that goes away, doesn't it? And then all you, yeah, I think you're probably overcomplicating it, yeah. So h goes to 0, it's gone, you just get g of x, boom. This one is the definition of f prime plus h has no impact on this, so it's just f of x, and this is the definition of g prime. So let me, that hidden zero is pretty powerful, isn't it? Like, how do you do that problem without the hidden zero? You can't do it, all right? So here's the conclusion. If capital H of x is two functions being multiplied together, right? Then the derivative of that is equal to g of x times f prime of x plus f of x times g prime of x. That's what we just proved, right? If you take the product of two functions and you want to know their derivative, that's what it is. Yes? Now, that's a nice little formula, isn't it? Unfortunately, that formula can be written in many different ways depending on who wants to write it down. Do we all agree that multiplication is commutative? You can always flip multiplication around, right? So if I wanted to, could I flip these and do f prime then g? And then over here I could flip this and do g prime then f? Or I could just leave them alone, right? Or I could flip this one, leave that one alone. Or I could do this, like put those over here, right? There's all these different variations that I can use. I have the freedom to use, right? Our textbook uses this formula. The formula our textbook uses is this. And on your reference sheets, this is reference page 5, and it's formula 5. So this is on reference page 5. Man, it's warm. Formula 5. And the way they write it is this. I want you to see the notation. d dx bracket f of x g of x. So what they're saying here, they're using a slightly different notation. Remember that notation means take the derivative, right? So this is just like that little prime has been, that little prime. What's the derivative of a product of two things? According to our textbook, it is f of x times g prime of x, and then plus g of x times f prime of x. Is that the same as the answer we just got with the proof I just did? Yeah, right? It's the same answer. It's not in the same order, right? What did they do? What did the book do? They just changed the order like that, right? But it's the same answer, right? So which one do we want to use? Do we want to use the one from the book? Do we want to use the one we got from the proof? Or is there other version we want to use? I personally do not care what version you use, but I will tell you the version that I teach, all right? I'm only going to teach one version, and you'll see why when we get to the next rule. I personally wish this wasn't here. I think this is a terrible way to teach it. It's just my opinion, all right? So even though that's the formula in the book, here's the way I would like it, and I'm happy for you to change this on your formula sheet. You can scratch out what's there. The version that I use is this. I do f prime of x times g of x plus g prime of x times f of x. That's the one I like. And I will have a reason why in a moment. I'm not just throwing that out there because, hey, that's what I like and you should like what I like. No, there's a reason why, and I think you'll appreciate it here in a moment. So let me walk through this with language, all right? Listen to my words here. Here I have the derivative of a product, right? So if I have f times g, the derivative is f prime g plus g prime f. F prime, then g, plus, then the g prime, then times f. So it's like they're taking turns. First, f gets the derivative, and g stays left alone. Then you add to that, now g gets the derivative, and f gets left alone. You see that? So let's go back to the example, the very first problem that I gave you, and watch how I'm going to do this. I had, what did I call it? I called it h of x, right? Was x squared sine x? Did I use little h? I did, right? Okay, let's go to that. And now let's talk about its derivative. The derivative of this should be, well, here's where we have to realize that we have a product, right? So I'm going to realize right here we have a product. And so if I'm going to use this rule, I need to assign one of these to be the f and the other one to be g. So I'm going to call this one f and this one g. And according to this formula, another way I could kind of write that is just to be like f prime times the g plus then g prime times the f, right? That's really what that formula is saying. Take the derivative of the f function, leave the g function alone, multiply them, plus now derivative of the g then times the f. So let's do this part first. I take the f function, which is x squared. I need to take its derivative, right? Then I will in the next line, times now the g function. The g function is just sine x, right? Then plus, now I need to take derivative of the g. The derivative of g is sine x. And then times the f function, but I don't touch the f function, so I just get x squared. These are primes, right? That's not to the first power, that's a prime. So I'm taking the derivative of f times the g plus the derivative of the g times the f. Now you can do these individually. What is the derivative of x squared? We said that that was just 2x, right? 2x. And then times sine x. Then plus the derivative of sine x, which we already had said was cosine x, and then times x squared. And we just have to be a little careful here because this does not mean x cubed, right? This x is trapped in the cosine. So this is actually just going to turn into 2x sine x plus, we usually like to pull the x squared in front of the cosine so that there's no confusion with putting the x's together. There we go. That's it. I'm going to go back to Desmos. I'm going to graph that function now, the answer we just got. It was 2x sine x, and then it was plus x squared cosine x. And I'll zoom out a little bit here. And let's see if it does, if the blue one is doing what it's supposed to do. So at 0, the red one has a flat tangent line, so the blue should have an x-intercept there. As I go to the right, the slope is positive. That's what the blue one's doing. Positive, 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 positive. Here, and am I still positive here? Yes, but what's happening when I come to this, I'm still a positive slope, but it's getting smaller until I reach the top, and that's where I have another x-intercept. So it does match. I mean, we could analyze this more deeply, but everything matches, all right? Okay, that's your product rule. Okay, the formula I gave you, that's the product rule. So now we theoretically should be able to take the derivative of any two functions being multiplied together. So let's do some practice. That was your first one. Let me put the formula on the side. Put the formula on the side off camera, but did I ever hit the record? I did, right? You saw me when?
Yeah.
I did. Do you see a red dot up there? Okay, it's blinking. Okay. So I'm going to write the formula down. I'm going to write it the way I like to write it. I like to write it like this. If you have f times g and you want the derivative, it's f prime times g plus g prime times f. To me, that's the most condensed, compact version of the product rule. And I'm using my order of things, not the book's. I told you I'd try and convince you why, but you're going to have to wait until we get the next rule, all right? So let's do an example. Let's say that I take some function, I'll call it h again, h of x. And let's say it's x cubed plus x squared plus 1. And then the other function is x to the fifth minus 2x plus 3. And I want to know the derivative of this. All right, so I'm asked to find h prime. Well, one thing I could do, right? One thing I could do is multiply all this out, right? Like imagine I did this times this, this times this, this times this, and then I do x squared times this, x squared times that, x squared times that, and then I could do 1 times that, 1 times that, 1 times that. That's called expansion. I could do that, it'd be 9 multiplications. I could get everything out, and then once I did that, I could just do the power rule on each one, couldn't I? Right? I could do that. And then I wouldn't need any product rule at all. But I have the product rule. And I see a product right here. And so to completely avoid doing any distribution like I just explained, I'm going to see that I have a product. I'm going to call this one F, and I'm going to call this one G. And when you look at F and G, can you find the derivatives of those individually? Do you feel comfortable taking derivative of that? Yeah, I can use last class. Can you take derivative of that? Yeah, last class. So now all I need to do is apply the formula. All right, so the derivative, according to the formula, would be the derivative of the f function first. So I'm not going to do it yet. I'm just going to write it down. I need to take derivative of that. Then times the second function g, but I'm not going to take its derivative. Then I add to that what g prime, which is the derivative of the second one, which I'm not going to take the derivative. I'm just going to write it with a prime. And then when I'm done with that, I need to multiply by the f function, which is this, and I'm not taking the derivative of that at all, right? Do y'all see how this works? It's not as simple as we wished it would be, but it's also not super complicated, right? It's like they're just taking turns with the derivative, right? They each get the derivative applied to them once, and then we add the two answers together. So let's do it. The derivative of this should be 3x squared plus 2x. What's the derivative of 1? 0. Okay, how many terms do you see here? 2. So I need it in parentheses, and then I'm going to multiply times that. Now, I'm not going to actually multiply that out. I'm just going to write it down for right now. Now, plus, now the derivative of this, which again, I can just use my rules. So 5x to the fourth minus 2, right? That's the derivative of that piece. And there were 2 terms, so I put it in parentheses. And then I do my x cubed plus x squared plus 1. Okay? That's the answer. Okay? This is what I like to refer to in this class as the raw derivative. The raw derivative, meaning that's the unsimplified, I'm not trying to do anything on that just other than showing you that I have the derivative. There's a ton of algebra that we could try here.